All right. It's about writing the actual equations and functions themselves. Looking at the roots and then the coefficients also. So we haven't really looked at roots a lot besides using the quadratic formula, right? And we've used our graphing program every time. So now what we're going to do is we're going to say, what if it's written in factored form? Right? Like what if an equation was written like this? Well, how could we do the same thing? We could multiply it out, and then we can distribute the 2. And then we can do everything in standard form. But when it's written in factored form, it's a lot easier than it looks. Right? It's much easier than what you have to actually do. So, in this case, what's something you would know from this? Your x-intercepts, or your roots, are going to be -1 and 5. Because how do you find the x-intercept? You set y equal to 0. So this would be a 0, you move the 2 over, you get -1 and 5. What else do you know? What else do you know? By the way, the general form is a, x minus root 1, x minus root 2. So this is a. So what else do you know?
It opens up.
It opens up. You know something else? You were here this morning, remember? You came for help? There's something I mentioned.
Yeah.
What else do you know? Do you remember?
I forget what it's called. But,
Show me.
it's like in between the one and
Good. What's halfway between the roots? What's the thing that's halfway between the roots always? The axis of symmetry. So if you found the roots as -1 and 5, you could just add them up and divide by 2. Find the average of the roots. That'll give you the axis of symmetry. Plug that back in to get the vertex. What else? There's another thing.
Wider.
What's it?
It's wider.
It's wider. Good. Well, no, 2 is narrower. Fraction is wider. Fraction is wider. What do you know, though, about the y-intercept? The y-intercept set what? Yeah, so the y-intercept is literally the product of the numbers you see. Take a look. 2 times 1 times -5. That's the y-intercept. It's a times r1 times r2. Okay? So that's literally the product of those 3 numbers there. Make sense? Okay. Now, the first part of these notes, I go through something called sum and difference of roots. I'm going to give you what the sum and difference of roots are. I'm not going to go through the whole derivation right now, just because I want to get through this and I want to be able to finish 7-7 tomorrow. I encourage you tonight to look at the video I've recorded already if you want to take down the derivation. So let's go. Okay, before we get to the derivation, we're going to look at these forms and I'm going to show you what I'm talking about. So again, I've already mentioned this, but here is standard form. We've seen this. Here is vertex form. The k could be over here, or the k could be over here on the left side if I subtract it, remember. Then the third form that I'm talking about is the one I was just mentioning right here. All right, this is called, I call it either root form or intercept form. It really doesn't matter. It's the same thing. Okay? So this is the last version of that. This is the first root, this is the second root, this is a. If you had x minus 7 and x minus 5, 7 and 5 would be your roots, which is why you see it in the form x minus r1, x minus r2, not x plus and x plus. All right? Because remember, to get the roots, you end up taking the opposite of this number. So if this was something like this, right? Remember, the roots are going to be 5 and 3. So literally, this is the root. This is the root. That's why you see the root is here and the root is here. All right? So this is, God bless you, this is the third form. Okay, the third form. Now, if we wanted to give you a starting point, the derivation of this is actually pretty easy. You'd have to multiply this out, though. And you're going to get a little bit, messy with subscripts along the way. But as a result of that, okay, if you solve, what you would get would be this. You would get the fact that negative b over a is called the sum of roots. And c over a is called the product of roots. So if you had something in standard form, right, and you knew a, b, and c, as a result, you would know what the sum of the roots are. So for example, let's take a look at y equals 2x squared plus for x minus 8. So what is negative b over a? Not 2a here again. It's not 2a. Negative b over a. What do you get for negative b over a? Negative 2. And then what about c over a? Okay, so it's negative 8 over 2. Well, that doesn't tell me much, or it doesn't seem like it tells me much. But what it does tell me, it tells me that if I knew the roots, I could check that I'm right by adding the roots together. And I should get this value. Because negative b over a was defined as the sum of roots. Then over here, c over a is defined as the product of roots. If I knew the roots, right, the roots must be probably like 2 and negative 2. Try and factor this. Tell me what you get. Or use your quadratic program real quick. Use your quadratic program. Make it even easier. Type in 2, 4, negative 8. We'll see more use of this in a minute, but I want you to start with that. Type in 2, 4, and negative 8. Negative 3.23. So add those two numbers together. Adding those two values together, you're going to get negative 2. The decimal portions cancel each other out, one being negative, one being positive. Right? This being negative 0.23, positive 0.23. And then negative 3 and positive 1 is indeed negative 2. What if you multiply those two numbers together? It's going to be an estimate, I'm guessing, because you probably had irrational roots, right? Are the roots irrational? Yeah. So take as many decimals as you can for now, but negative 3.23, do a few more, and multiply it by 1.23 with a few more. You should get negative 4. Okay, I'm going to go over some applications and uses of this, and we're going to see how we can use them if we know the roots to come up with an equation. But for now, I just want you to understand that this is true. That negative b over a is the sum of the roots, and that c over a is called the product of the roots. I feel that sometimes the derivation kind of confuses people more than anything else. And they get bogged down on it because it's a little bit tricky. So if you can just remember this for now, that's okay. If you want to see the derivation and write in your notes, I encourage you to just look at the video and see what it is. But for today, like in class, I want you to remember these two facts. That negative b over 2a is the sum of roots and that c over a is the product of roots. All right, and let's look at an example of how we can use that now. We have two roots that are imaginary. If roots are imaginary, it clearly means that the graph either floats above the axis somewhere or floats below the axis opening down. I know that already. But knowing these two roots, it's tough to figure out what the equation is. Right? I can't write like x minus r1, x minus r2, and then multiply it out. Because look at r. Isn't r imaginary? Right? We have this. We know this already. Right? Does everybody agree? That's what we just wrote in the last slide. This is intercept form. If the intercepts were 3 and 2, wouldn't this be very simple? Wouldn't you just plug in a 3 here and a 2 here, and then somehow you'd have to figure out a if maybe at another point? We'll talk about that in a minute. What if they're imaginary there? You can't really plug in imaginary there. It'd be so messy to have to FOIL that out with imaginary parts. So instead, what should you do? You have the roots. You have the fact from the last slide about sums and products. So what should you do with the roots? Not rationalize them, no need to. Think about the information you gained from the last slide. What can you physically do with these roots that would be useful from the last slide? Or, thank you. So add the roots together. We said a minute ago that negative b over 2a is called the sum of roots. So add them together so we can write something in place of the word sum of roots. What do you get? Common denominator, right? So keep the denominator the same. 3 plus I plus 3 minus I becomes what?
Isn't the negative b over a is the sum of roots?
Oh, thank you. Thank you. I put a 2 there. Please cross that off. See? I even forget that one. Okay, remember that's just a. I did the axis there. Okay. What is it?
3.
You're going to get 3 as an answer. So Because you're going to get 3 plus I, 3 minus I, giving you just 6 in the numerator, right? And then the denominator is still 2. So again, when I sum these together, I get 6 over 2. Now, I'm going to leave it as 6 over 2 for a moment. Is that all right? I'm going to leave it that way for a moment. I'll explain why next. Then I want to multiply them together. 3 plus I over 2. This needs a little bit of work. Times 3 minus I over 2. Multiplied. So the numerator, complex conjugates. The middle terms cancel. Please don't do the middle terms. So start foiling, but ignore O and I for FOIL. So you're going to get a 9 minus I squared all over 4. You don't need to really FOIL that because the middle terms cancel. I squared is negative 1. 9 minus negative 1, Mike, is?
It's negative 9 over 4.
Not negative 9, we're subtracting.
Oh, 9 minus negative 1.
So what do we get from 9 minus negative 1? Not times.
10.
Yeah, over 4. Now, reduce that by, first thing you reduce it to, becomes 5 over 2. And what you recognize now, the sum of roots, wasn't it 6 over 2? Right, wasn't the sum of roots 6 over 2? And the product of roots is 5 over 2. They're both over 2. So what do you suspect A is? 2. Because they're both over 2. So ready? Let's write this out. We get negative B over A is 6 over 2. And we get the fact that C over A is 5 over 2. Remember, this is the sum of roots. This is the product of the roots. So as a result, it's clear to us that A has got to be 2 if we're looking. Now, in a lot of these problems, it's prefaced with, find a function with integer coefficients. You're going to see that a lot. So had I done this, right then, had I made this 3 over 1, it would have made A1 over here, right? But then this would have been 2.5 over 1, wouldn't it? So that would have made C 2.5. Is 2.5 an integer? No. So we're going to usually leave it in unsimplified form, or if we do simplify it, that's okay. We just have to multiply it at the end by 2. So if I didn't do this, let's do it 2 ways, okay? So I can start by writing it this way. Clearly, we're going to get A is equal to 2, B is equal to negative 6, and C is equal to 5. How do I know B is negative 6? Because negative B is positive 6. So positive B is going to be negative 6. And as a result, I get the following. Now, had I reduced my fractions, I'm going to use green ink. Had I reduced my fractions, this becomes 3, this becomes 2.5. Now, if that were true, then all this would do for me, I'd have to assume A is 1, because I don't know anything else. I know that this is 3 over 1, and this is 2.5 over 1. So I'd have to assume that A is 1. And you would get a function that looks very similar. It looks like this. Right? If I assume that A is 1, because this is really 3 over 1, that makes A 1. B, as a result, would become negative 3. C is this right here, which is 2.5. So what's the only difference between these two functions? Yeah. This one in red is double the one in green. It doesn't really matter unless the problem specifies and says integer coefficients, which it probably will. Okay? It probably will. Did this one say it? It did. This one, the title was find a quadratic equation with roots 3 plus I over 2 and 3 minus I over 2 that has integral coefficients. Integral coefficients simply means that they are integer values. Alright? So for this one, I'm just asking you to find the roots. So find it on your, find it actually this time with a quadratic formula real quick, and then verify that this is true. Just a simple verification. So quadratic formula, you should do this like, and seriously guys, 30 seconds, tops. Quadratic formula. Okay, y equals, it's not x, it's y in this case. Y equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Now, we're going to get negative 1 plus or minus the square root of, that's going to be 1 minus, what is it going to be, 1 minus 40 or plus, because we're going to get a double negative. 1 plus 40 to give us 41 there over 4. What do you recognize? The roots, again, are conjugates. The fact that they're conjugates makes life easy on us, because when you add these roots together, the conjugate portion cancels, just like it did a minute ago. So let's verify that these roots are correct. The sum of them looks like this. Right? That's the sum of the roots. We're not multiplying, I'm just putting parentheses to make it look neat. Negative 1 and negative 1 in the numerator gives me negative 2. Root 41 and negative root 41 cancel each other out when you add them together. Remember, when there's a common denominator, you just repeat the denominator. You don't add the denominators. I see mistakes on simple arithmetic a lot with this. So you get negative 2 over 4. Or simply negative 1/2. So that's the statement I can draw from that. The sum of the roots, which is negative b over a, is equal to negative 1/2. What about the product of roots now? What about the product of roots? And you can check, by the way, that that is true. Look, what's negative b over a? It's negative 1 from b over a, which is 2. So it's negative 1 over 2, which is what we got, negative 1 over 2. The product of roots, what's going to happen? Why does it make it simple? Or why is it the fact that it's binomial conjugates make it simple?
The roots cancel? Or the middle terms?
The middle terms cancel here. The middle terms cancel. So you start by foiling, but you don't have to worry about the middle terms. So negative 1 times negative 1 is going to be positive 1. Middle terms cancel. Root 41 times negative root 41 is negative 41 over 16. 1 minus 41 is negative 40 over 16. If I divide them both by 8, I get negative 5 over 2. Now, isn't this c over a? That's the product of roots. The product of roots is always c over a. And c happened to be, in this case, I think, I'm pretty sure, negative 5, if we scroll back up. Yeah, there it is. C was negative 5, a was 2, so it's negative 5 over 2 for c over a, and lo and behold, we get negative 5 over 2 for c over a. All right? Very simple, but just to prove that it's true, to check. Let's see if I want to go one further. Let's finish with example 3 to end today. So we want to find a quadratic function with a minimum value of negative 3 whose graph has the following intercepts of 1 and 3. What could you do to start this? Could you visualize it maybe? Would that help? So let's do that. Intercepts are 1 and 3. And the minimum value is negative 3. The minimum value means what? What's another word for the min or the max? The what? The vertex or extrema. Very good. And its value is negative 3. So that's somewhere along this line right down here, right? At negative 3. Well, where's the axis of symmetry right now?
2.
At 2. Well done, Ryan. At 2, right here. So if I look at these two, if the minimum value, remember the word value means the y-coordinate, is at negative 3, and I know that the x-coordinate is the axis of symmetry, just find out where those intersect. There's the vertex right there. Since the value is down at negative 3, I know that this coordinate must be something comma negative 3. Well, the question was, what's that something? That something is halfway in between the roots. So that something turned out to be 2, as Ryan said in this case, the axis of symmetry. Again, this coordinate is 3, 0, and the other one is 1, 0. But does that really help me come up with a function? What does that help me come up with? A graph, right? Go to your general intercept form, please. You know R1 and R2. What are they? What's R1?
1,
And what's R2?
2, -2.
No.
Or, yeah, positive 2.
Yeah, so I'm asking you what they are. You're right. The function turns out to be minus, though, yes. Remember, if you were to solve this, wouldn't this give you a root of 1 and this give you a root of 3? So always think backwards how you would solve it. So x minus 1, x minus 3. How can I figure out the a value? I have some other piece of information from my graph. What piece haven't I used from my graph? I used the roots. What's the other thing on the graph, people? The axis of symmetry or the vertex. Because remember, to get a, I need to know what x and y are, and I can solve for a. Here's x and y. If the point is on the curve, it satisfies the function. We've said this all year long. If there's a point on the curve, it satisfies the function. -3 equals a times 2 minus 1 times 2 minus 3. Solving for a. We're going to get a times 1 times -1. And as a result, we're going to get -3 equals -a. So a, therefore, equals positive 3. So my equation at the end, or my function, looks like please finish it off by just graphing this real quick on your calculator. Okay, graph this last one in that form and take a look to see that we were correct. Okay, match that up with the graph that we drew in the beginning of the problem. It clearly seems to be right because it opens up. And we drew a picture of a graph that opened up. So A had to be positive. If you got a -a for this, you need to stop and say, what did I do wrong? I made a mistake somewhere. I put in the wrong signs. I switched my root signs. What was the problem, right? So go ahead and just graph this and take a look. And what you'll see again is that your vertex is at 2, -3. And that the roots are here and here. And you should see a graph opening up. That looks something like this. Maybe a little bit more curved than my ugly graph there. Okay? Does that make sense what we did to start this lesson off? So tonight you're completing homework 7-6. Alright? Tomorrow we're going to finish 7-7 and you're going to do homework 7-7 tomorrow night. Remembering though that the test is not until Wednesday. So on Friday we're going to start the catapult project. Ooh, I saw that going down. On Friday we're starting the catapult project. On Monday, we're going to review. On Tuesday is Ignition Awareness Day. On Wednesday is your test. Thursday, you're off. Friday, we finish the catapult project. So once we finish 7-7 tomorrow, we're done with the material for the test, really. Okay, so you need to make sure that if you're confused right now on the stuff we've been doing with 7-6, anything, and then anything with 7-7, just come see me before next week. Please don't wait till Wednesday morning when the test is on Wednesday.
So, the only problem is 7-6 and 7-7.
Yep. Problem sets are short for this test, okay? But remember, guys, these homework problems and these problem set problems, they take a while. Because you have to do every time. Vertex, x-intercepts, y-intercept, axis of symmetry. Does it open up or down? You have to do all this work each time. A little louder.
On 13th, Friday, I have softball.
You do, that's correct. So, that's all right. We're just finishing up the project today, so I can go over with you. Okay, that actually works out better that the test is not Friday then. Because that wouldn't have made sense then. Okay? All right. So we start with this chicken pen that's alongside of a house. So we always start by drawing our barrier first. There's the house. Bird's eye view. This is our dimension here. We can call this W, call this W, call this L. Now, we're told that we have 60 meters of fencing to use. What kind of a constraint is that? These are terms I'm using on purpose. The word constraint is something you're going to hear in calc. You have constraints. Those constraints limit you to a certain specific set of answers.
Is it the max?
Max what? You're on the right track. The constraint of 60 meters is a maximum something.
The maximum fencing you use.
Yeah, the maximum amount of fencing you can use, not the max area, right?
Yeah.
So you can't just say the max because we're trying to find the max area. So in this problem, what equation can I write already from the given diagram and the fact that we only have 60 meters of fencing to use? What could I write?
LW equals 60.
LW, that's area, right? LW equals 60 would mean that the area equals 60, right?
2W plus L equals 60.
2W plus L equals 60, perimeter, right?
Yeah.
And if you didn't know that, or if you forgot, look at your units. If that doesn't say meters squared, it's not area, all right? If it says 16 meters, that's a linear, or it's a distance or a length. Okay, linear dimension. It's not a two-dimensional spot where you're looking at area. Do we have enough information to solve right now? Do we have enough information? Why are you shaking your head no, Niall? What do we need? What small piece do we still need?
You need to figure out if you can't solve the equation for a number with two variables.
Okay, so we have two variables. We can't do that. So what's the other equation that we're going to use? And this is interesting to write because we don't have a lot of info about this other equation. But Niall kind of started us off with that part. Say again? Yeah, so let's write WL or LW equals, let's just call it capital A for area. X is fine, but just not confuse with X and independent variables. So this is the area function, right? W times L. Well, this is the perimeter function. 2W plus L equals 60. What do you always do when you have two equations and multiple variables? What do you always do? Yeah, you always use substitution, especially because here you have a product of W and L. You cannot use elimination here. So looking at the first equation, what's the easiest thing to solve for in the first equation? Why?
Because it's just plus L and there's a 2 with W.
Yeah, but L is by itself, please. So just get rid of the 2W. Move the 2W over by subtracting it. This becomes L equals 60 minus 2W. Whenever a variable has a 1 as a coefficient and you're using substitution, again, solve for that variable. It makes more sense. Solving for W would be annoying as anything. You have to subtract L and then divide by 2. Doesn't make sense to do more work. All right, so that's the expression for L. What do I usually do when I solve for one expression? What do I do with it then? What do I do with it afterward? Charles?
Plug it into the other one.
Yeah, plug it into the other one. Hence the name substitution, right? You're substituting this in for this. So as a result, we get the following. W, parentheses, 60 minus 2W, close parentheses, equals area. So what does this look like? What does this look like to you? This is where you have to think about like recognizing the nature of functions and equations. What do you see when you look at this? What do you see when you look at this? Kelly? Yeah, I see a quadratic also. Because think about it. Distribute the W. What do you get here? When you get 2W squared? So I'm seeing a quadratic for sure. All right, now, we want to find out what the maximum area is. Area is like what coordinate in my quadratic if I look at this equation here. The area is in place of which coordinate, x or y?
Wouldn't it be C?
Say again?
Oh, C is like,
What does C mean?
um, Y
Good. Or the y, not intercept, the y value.
value.
Okay, the y-intercept is C at the end of it. The area here is unknown. This is like saying the following. Ready? Distribute the W, you get this. And then putting this in standard form, it looks like this. And I'll put the area on the other side. I'm going to put area on the left-hand side. It makes no difference. And take a look at this now. The area of this rectangular chicken pen or whatever it is a function of the width now alone. We have eliminated the length. The area function is only a function of width. This is like saying y equals negative 2x squared plus 60x. It's literally the same thing. Just have different variables there, right? Instead of that, you have a y instead of an a. If you want to find out the maximum area, it's like you're finding the maximum y value. Well, how do I know there's going to be a max for this graph? Why isn't there going to be a min? There could be a min, right? Why is this one going to be a max? Correct, but certain problems, you don't know which one will work out. Use the equation to help you. A is negative. When A is negative, the graph is clearly going to open down. So you have some sort of a max point. Maybe it's there. Maybe it's there. Maybe it's there. It's not going to be negative. We can't have a negative area. So I know that the graph has got to be a vertex above the x-axis somewhere. So our goal is to maximize the area, or therefore find the vertex, the maximum value. We'll get an x value and we'll get a y value. The x value is like my w, my width. The y value of the vertex is the area we're looking for. How would I find the maximum value of a function? Is where we have to go back to what we learned. Maximum value of a function, what would you do? How to find a vertex of a function in standard form? Yeah. So guys, it's the same thing. It's the exact same question. If you want to find the max area or the maximum of a function, you need the axis of symmetry first because it's the vertex.
Would you set A equals 0?
Would you set?
A equals 0?
No, because then you'd say the area is 0. We're trying to maximize the area. By putting a 0 there, you would get the roots and you'd get the x-intercepts, but that wouldn't help us much. We're trying to find the vertex only. So to find the vertex, we do what Niall said. We say axis of symmetry equals negative b over 2a. Why did I put w? Why did I write w equals negative b over 2a? What's it mean?
Because the W is serving as the X value.
The w is a placeholder for where x should be, right? This should say, if we thought back to what we had in the last section, we could think of this as y equals negative 2x squared plus 60x. Okay, that's literally what it looks like for us, or that's what we should be thinking about. Same thing. We would say x equals, we're going to say w equals. What do we get as a result? What's negative b over 2a going to give us? 15? Now, that is the x-coordinate of the vertex. The question is to remember, what is the y-coordinate? Okay, think about the function we started with. This is written as the following. W, comma, a. Width is the x value. Area is the y value. That's what we have from this function. W is the x-coordinate. A is the y-coordinate. So this is the width of the rectangular pen. We know that already. If we know the width, we also know the length. We could find the length and the width, multiply them to get the area. Or what else could we do to find the y-coordinate?
Plug in 15.
Plug 15 in where?
So in that equation.
Yeah, into the area function. So let's do it that way, and then we'll prove both ways work. So we take the area function, evaluate it at 15, which gives us negative 2 times 15 squared plus 60 times 15. What does that yield as an answer? What does that yield as an answer? For what? 450? It looks like negative 450 plus 900, which should be 450. Right? Now, let me make sure you're right before I go on. Yep. Now, as a result, we know that this is the area of the function or of the rectangular pen when the width is 15. Well, if you go back to your original statement and check that makes sense of it, watch this. You know that this was the diagram. If these are 15, and the overall length of fencing was 60, 15 and 15 is 30, what's left over for this? Another 30. And then if you want area, area is length times width. 30 times 15 is 450. All right, so that's my maximum area, 450 square meters. So if you're writing down some notes to yourself, some steps, one thing I would jot down is you want to solve for the maximizing function in terms of one of your independent variables. Because remember, we had L and W. Couldn't solve for both. We couldn't do this problem involving both L and W. So we solve for the maximizing function, meaning solve for a, in terms of one of the variables. So we had a function that said a equals negative 2w squared plus 60w. That was the goal, to get that. Once you get that function by itself, to maximize it, find the axis symmetry, and then find the vertex. Or minimize it, right? Depending on the problem. Let's see another one of these. Ball thrown vertically upward with initial velocity of 12 meters per second. Its height is given by that function there. Determine how high it will go and after how many seconds will this occur. So what are we going to do for a problem like this? Mike, help me out here. What could you do to start? What piece of information might you be able to use? What can we write to start? What's the starting point or something we know? Plug 12 in for? What did you say?
Velocity.
For velocity. That works, yeah. You can take this 12 and plug it in for V0. Writing the following. H of t equals 12t minus 4.9 t squared. That works. I think that's a good starting point, right? Because now, what do you notice? What are we trying to find the maximum of in this problem? What is the problem asking us to find the maximum what? Maximum height. Now, height a moment ago was a function of time and VO. Look at the original equation in the actual problem. Time is one of the variables and V0 is one of the variables. Well, we plugged in for V0 so we could get height as a function of only one of the independent variables. Forget V0 now. And as a result, we're going to approach this the exact same way. Let's write it in standard form first. And then go ahead and find your axis of symmetry and find your maximum height as a result. You definitely need your calculator for this. So we get, right, x equals negative b over 2a. But in this case, it's not x, it's time, right? Time is our independent variable. So go ahead, plug in your negative 12 over 2 times negative 4.9 and see what you get as a result. After how many seconds does this projectile reach its maximum height? Ben, what do you got for me? What's the time again?
For the first equation, negative 12 over 2.9.
What do you get as an answer? 12 over what'd you say?
2.9.
Doing negative b over 2a? Right here?
Yeah.
2 times 4.9 is going to be 9.8. So it should be negative 12 over negative 9.8.
Oh yeah, I think it's like this now, sorry.
That's all right. What do you get as an answer though?
So
Is your calculator on fraction mode or something? Is that why you're giving me a fractional answer?
I don't know why you did that.
It's all right. What do you get as a decimal answer?
1.224.
Yeah. All right, so around 1.2 seconds. Remember, you're solving for the axis of symmetry, which really says x equals, which in this case is t equals. So part of this question was find out the max height of the projectile and how long it takes to get there. Well, you've done half of it. This is how long it takes the projectile to do this and reach its max height, 1.2 seconds. What would the total length of the flight be then? Side note question, right? What would the total length of the flight be? From start, back down, finish it, land back on the ground. We've done this already. Hang back. What would the total length of the flight be? Why?
Because it takes 1.2 seconds to do its maximum.
Yeah, the symmetry of projectile motion always. 1.2 seconds up, takes 1.2 seconds down. Yes?
So wouldn't it go faster on the way down?
No, believe it or not. I know you think it would, right? Because the fact that you're saying, well, gravity's pulling it down on the way down, right? It's got initial velocity fired up. So the initial velocity it's fired with was compensating for that negative effect of gravity on the way up. I know, right? It's counterintuitive because of gravity, but it actually is at the same time. Right.
But wouldn't it, like, once you reach the top, didn't it also go slower and then goes back down?
No, so what happens is this, guys. It reaches the top, it stops instantaneously. Then it has to pick up speed, pick up speed, pick up speed. By the time it hits the ground, it's hitting the ground with a speed of negative 12 instead of positive 12. So it's literally symmetric. It's identical on the way up and down. You'll learn about this in physics, actually. Now, in real life, with air resistance included, air resistance can affect it a little bit, but gravity, gravitational forces, are not going to affect it. It's symmetric in itself. Okay, if you have to take air resistance into consideration, it might vary by, tenths or maybe a little more, 2-3 tenths of a second, whereas here it's not going to.
If it wasn't a ball being thrown up, like if there was something with like an unbalanced weight on either side, would that change it?
Only air resistance would affect it still, but gravitationally, no, absolutely not. Let's take the experiment. If there's no air resistance and you drop a feather and a bowling ball, they will literally fall at the same rate. You can YouTube and watch a video of it. It's kind of cool. People have they have huge vacuums where they suck all the air out of it. There's literally no medium, so there's no air resistance. You can drop a bowling ball and a feather, they will fall at the same rate. It's air resistance that changes the rate things fall. These kinds of problems, again, we've been studying all year, we've never included air resistance. And even in physics in high school, you're not going to. If you study college engineering, you will. In college, air resistance is a differential equation. It's a function of its velocity, it's a function of surface area, it's a function of material, it's a function of volume, I think is the last thing. There's like 4 or 5 things. Okay? In reality, temperature affects it, wind speed, all that other stuff too. So there's a lot more to it than just this. Well, if that's the time it takes to get to the top, we can plug that time in for here and see what the max height comes out to be. So let's do h of 1.2. So find the height at or after 1.2 seconds. That's what this is saying. What do we get when we plug in a 1.2 into our height function?
I got 7.347.
7.34. Or 35, I guess we'd round to if we're doing that. And we're in meters, right? Because we were in meters. Yeah, meters per second for our initial velocity. So it's about 21 feet. All right? More, obviously, a little bit because a meter is greater than 3 feet. A yard is exactly 3 feet. Okay, that's our maximum height this object can attain. If you were drawing this again, right, it would be launched upward, reaches the top, and then it comes back downward like this. This height is 7.35 meters. That's what's physically happening in this one. The process is the same for all these problems. So the second part of 7.7 is about maximization and minimization techniques without calculus, right? So minimizing and maximizing functions using simple, or I guess rather simple algebra. Here we're looking at production cost. So don't even read on. If you're looking at the cost, what do you think you're going to probably want to do? Find the minimum. You're going to want to minimize your cost, as a result maximizing your profit. So if the production cost function developed by workers at a video game company is represented by C of n equals that equation or that expression, where n is the amount of games sold in millions, C of n is the company cost in $10,000s of dollars, determine the amount of video games that should be produced to minimize the cost, and then figure out what is that cost. Try this on your own. Try this on your own. You're given a function to start with. You want to find out the minimum cost, but you also want to find out how many games must be produced to get this minimum cost. I'll give you about 3 minutes. Try to come up with your answer. Think about that coefficient A and what you can do with it to start this problem. you're struggling, start by distributing A. Start by distributing A. Anybody a Terminator fan? Terminator, the movies? Or the actual head for the bad guy in Terminator? Just be careful. Because, at least it's something. The thing from, is that from, Dr. Who? He did South Park at one point. Yeah, that's Mr. Richard. You just download it. Yeah, it's a machine, right? Is that what it's called? Is that an English word? That's not. How do you know, by the way, it's going to be a minimum value you apply to this problem? How do you know it's not going to be a maximum? Like, why is the vertex a min and not a max? Right?
Well, because you don't want it to, you don't want the, whereas the possibility of getting into the want to be high.
Okay, that's a good logical reasoning, right? Logically, you want the cost to go down, so you're minimizing. But tell me from the problem specifically what tells you that you will not have a max. You will have a min for sure. Like, why do we have a min for sure? Because what? Because A is positive. Remember? When A is positive, the graph opens up. When the graph opens up, you have a little valley at the bottom there. How do you spell this word?
T-A-R-D-I-S.
I thought it was like tardy means late or behind time. It's about time travel.
Yeah,
I'm trying to look at the root of the word, thinking maybe that would
but it means time relative to dimension in space.
well, if he had the first half, so it's only the second half or something. Because there's other half signs out there.
Okay.
So for now, just bring this, and when he brings that, when he's at the next, we can see what.
Okay.
Did you post their grades on Dropbox?
Yeah.
You can do it.
Yeah.
For, for the problem sets, for problem set 6, 7. All right, so let's take a look. Can somebody step me through the process they took? What do you have for me?
When you distribute 2.1, it becomes 2.1n squared minus 7.35n plus 9.87.
What, plus what?
Plus 9.87.
And what was the first step in this, Luca?
You just find negative b of 2a.
Yeah, go ahead and find negative b over 2a. Again, why are we doing that? Because this graph looks like the following. I don't know specifically what it looks like, okay? I'm just opening up parabola. Maybe it looks, it can't look like that. That was dumb. You can't have a negative vertex here because the cost can't be negative. I mean, could, I guess, but that wouldn't make sense. I mean, that you were like getting money to make it and not having any cost. So let's say it looks like that. You're only going to be really looking at the first quadrant because n is the number of games, c of n is the cost. So we really don't have to even worry about these quadrants over here. Can't have a negative number of games, and you can't have a negative cost. So you should know that it'll definitely be in your first quadrant. So we find the axis of symmetry because we want to figure out what the vertex is. And the vertex is right here on the axis of symmetry. So as Lucas said, we're going to use n equals negative b over 2a. I use n instead of x because n is along my x-axis now. Negative b, or negative 7.35 over 2 times 2.1. What do you get for that when you do that?
1.75.
1.75. Now, that's the number of games. Is it 1.75 games? Sabine, what is it? You're shaking your head. Yeah, because it's in what? In millions. It's 1.75 million games. So 1,750,000 games is the n value. Now, the thing is this. You're going to use 1.75 and plug that in, though, to the function. You're not going to use 1,750,000 because the function is in terms of millions. So you just put the number you get, 1.75, in for n. So let's find the cost to make 1.75 million games. This is a decimal right here. What do you get for this? When you plug 1.75 in. And again, make sure you're using a calculator, obviously. You're not going to do this in your head. I'm going to go with that many decimals. The reason I'm doing that is because this is in 10,000s of dollars. So what does that mean? Like this was the number of games, we got that. We figured out how to do that with the millions. How do you convert 3.43 in 10,000s of dollars? What number does that mean? Like if you had 10,000 of dollars, right? If this answer came out to be 1.0 $10,000, it would just be 10,000. If this was 2, it would be 20,000. So what is this one going to be? 34,388. Okay, we have 3 10,000s, which is 30,000, and 0.4388 10,000s, which is 4,388. So again, it costs 34,000. Now, do me a favor, what's the average cost? What's the average cost per game? Check it out. What's the average cost per game? This is manufacturing only, folks. This is not research and design, obviously. If you only cost this much to everything, nobody would ever pay $60 for a game. You pay $60 for a game because you're paying for the research and design that goes into that game. But here, right, what do you get cost per game? $50.88. And sure. What did you divide?
34,388.
Somebody help me now. Tell her what she should do differently. One thing's differently. Well, 2 things I can think of. Remember what I said, find the cost per game. What should my units be? If you're looking for cost per game, what should the units be? Dollars per game. These are dollars. These are games. So you should be dividing this by this.
About 2 cents.
Yeah, it's $0.02 per game. You take this number, 34,388, divided by 1,750,000. You're going to get $0.02 per game. $0.02 is 2 cents per game. That's literally, this is not like an exaggerated number. That's what it really does cost in manufacturing. You don't pay for production for a lot of things. And who has the new Xbox One? Anybody have the new Xbox One or the new PlayStation? Do you know what they do now? Do you actually buy games anymore? Xbox One, you don't get a disc anymore. I don't know about PlayStation. You actually get like a redemption code. Remember how on Xbox Live you put in a code? You get a redemption code, you plug it in, and you just download the game as like an app. Because of the fact that it doesn't make sense to even produce the game anymore, yet it's still only 2 cents to make a game. You pay for the research and design when you ever do things like this. Remember your homework is 7-7 tonight.